students, and welcome to another session of EE102 mentoring online. I am Rajranath, and I will be discussing today about the basic laws, especially using node analysis and mesh analysis. So this presentation, if you will have any questions, as we will be looking at 4 examples that will help you in your exam that is coming up. Okay. Alright, so as you can see, this week what I have prepared is 2 of the fundamental methods that are discussed in EE102. Okay, so this is when we actually start to look at the real electrical part of calculations, especially circuits, because from now onwards we will be looking almost every time now we will be looking at circuits. Okay. So first method or first thing that we need to discuss is a nodal analysis. Okay. So in case someone is wondering what is a nodal analysis or what it is, so it's instead of focusing on the voltages of the circuit elements, one looks at the voltages at the node. So what it means is, okay, let's say this is a node, okay, meaning you have your circuits going on with the resistor this way. Let's say this is a resistor this way, and let's say this is what gives you like a supply. Okay, this here is known as a node. This point here is known as node. Okay. Okay, so in a given circuit with the n amount of nodes, meaning no matter how many nodes are given, without voltage sources, the nodal analysis is accomplished in 3 steps. Okay, so first we select the node as a reference node. So we need to assign, let's say, node 1, node 2, node 3, these 3 junctions. So we'll be assigning it as node 1, node 2, and node 3. Okay. And also okay, so first step, like what we said, was to assign the reference nodes as V1, V2, and the remaining of the nodes. And for step 2, it is apply KCL. Okay, so KCL basically means that on a certain node, okay, let's say this is this node. So KCL means I have to assign different direction of currents. Okay, that is leaving a junction. You know how the rule is about the sum of current entering a junction is equal to the sum of current leaving. So that is what KCL means. Kirchhoff's current law. That's what it states. Okay. So and then we will use Ohm's law to express the branch currents in terms of node voltage. Okay. So in this node analysis, we work with current to find voltage. Okay. So solving the resulting simultaneous equations to obtain the unknown node voltage. So you have to remember that the current, it usually flows from high potential to low potential. Okay, so this formula is really important. This formula actually helps us to really understand what we will be doing. Okay, because usually previously we've been looking at mostly with circuits with only like 1 voltage supply. However, since now we are using nodal analysis, we will be using with 2 or 3 different voltages. Okay, so this formula is really important. Now, to help you better understand on what it means, we will focus on this example. Okay, so let's say a question is given. It says determine the voltages at nodes. Okay, so this is node 1, node 2, and node 3. Okay, so if we go back to our steps, it says select the node as a reference node, assign v1, v2, v3. Okay, so that's what I have just done. So this is my 1, my 2, and this is my 3. Okay. Second step, which is apply KCL. Okay, so it has already been done for us here on this side. Okay, so one is the current supply, so that's one direction, and these other remaining directions is my own assumption. Okay, this is what I assume, that this is how the current is flowing. Okay, so as you can see, the sum of current entering the junction is equal to sum of current leaving. So what it means is, to solve the result, so we have to express this using Ohm's law, and then simultaneous equations to solve. So before that, Ohm's law, so we have to do V is equal to IR. So I is equal to V upon R. Same thing as this formula. Okay, same thing as this formula. So the sum of current entering in node 1 is 3. Okay, sum of current leaving is Ix. Okay, Ix has already been given to us in the question. So Ix and I1. Okay, so 3 is equal to Ix plus I1. Okay, now let's look at node 2. In node 2, so sum of current entering is Ix, sum of current leaving is I3 and I2. Okay, now for node 3, sum of current entering is I1 from here, I1 and I2. And sum of current leaving is, we can say this is 2Ix. Okay, this is node, this is a dependent source, meaning whatever the value we will find for Ix in this branch, we multiply it by 2 to get us the value of 2Ix. Okay, so whatever value we multiply by 2 will give us the current value that is going through this branch. Okay, from node 3 to your ground voltage. Okay, so now if we look at it, okay, so okay, set. Okay, so now if we look at it, so at node 1, as I said, 3 is equal to I1 plus Ix. Okay, so for for I1, how did we get this value? If we go back to our example, so I1 is this one. So high potential minus low potential over the resistor value. So V1 minus V3 over 4 ohms. So V1 minus V3 over 4 ohms. For Ix is the same thing. For Ix is the same thing. V1 minus V2 over 2 ohms. So V1 minus V2 over 2 ohms. If we look at node 2 now, node 2 the equation is Ix is equal to I2 plus I3. So if you follow the same principle, Ix will be V1 minus V2 over 2, I2 is V2 minus V3 upon 8, and I3 is V2 minus 0 upon 4. Now why 0? V2 minus 0. 0 because the ground voltage, because current is I2 is going from, I3 is going from V2 to ground. So that's why it's V2 minus 0 upon 4. Okay, so you have this. And then at node 3, you have I1 plus I2 is equal to 2Ix. Now V1 minus V3 upon 4, and then V2 minus V3 upon 8, 2 into V1 minus V2 upon 2. Note that this 2Ix was considered, however, the value of Ix is just V1 minus V2. How is that? Okay, so if you go back and look at your example for Ix value from the original equation, which is this one, is given as V1 minus V2 over 2. Okay, so if we multiply this by the value of 2ix, which is 2, then these 2 and these 2 cancels, so you're left with only V1 minus V2. That is what has been used here. Okay, so it has already been solved. Okay, so after that, then you have to solve this using matrix. Usually what we use is Cramer's rule, and if you use Cramer's rule, then you should be able to get this as your answer. Okay. Now let's look at another example, which is supernode. Supernode means it's when there is a voltage source between two nodes. Okay, like this is an example of a supernode. When a supernode happens, or when you identify something as supernode, whether dependent or independent, what happens is you take that part out, similar to what has been shown below. Okay, and then these two nodes are seen as one. Okay, so what I mean is, generally when you look at it from here, I do I1, I2, I3, I4, and I5, I6. Okay, so these are two separate nodes. But once I take this voltage source out, I will look at these two nodes as one, meaning whatever current will be entering here and here, I'll add those two. Like for example, in this case, for both of these two nodes, sum of current entering is only 2 amps. And sum of current leaving is I1, I2, and 7 amps. Okay, so this is given as one equation. Okay, that is one equation, right? And then note that the normal formula to how to find current is still the same. We will still use the same formula. Okay, like for I1, it will still be V1 minus 0 upon 2. For I2, it will still be V2 minus 0 upon 4. Okay. Once this is done, then you will have another new circuit. Not actually a new circuit, it is the supernode circuit that you will be using. Okay. So in this, what you do is, for the two nodes between where the voltage source was, you add a plus and a minus, and you just go around as a closed loop function. So as you see from here, okay, this is minus V1, minus V2, minus V1, minus 2, plus V2. Okay, minus V1, minus V2, plus V2. Okay, so as you can see that this is the equation that you get, and then you solve these two simultaneously to get the answer, and you should be able to get that as the answer. Okay, so once this is done, so this is the only difference for supernode. It's whenever you see a supply, a voltage supply between two nodes, that is known as your supernode. And note that if there is a resistor that is in parallel with that supply, okay, you take that out as well, like it's been removed here. Okay. Now let's look at another important method, which is mesh analysis. So you know how we used we were using current to find voltage. In this case, we will be focusing on voltage to find current. Okay. So what I mean is, so first of all, what is mesh analysis? Okay, so mesh analysis is just Kirchhoff's voltage law to find unknown current. So that is what I just explained. And mesh analysis is limited to one aspect. It can only apply to circuits that can be rendered planar. Okay, so it needs to be a closed loop circuit. Okay, a planar circuit can be drawn such that there is no crossing branches. Okay. So how to determine mesh currents? Okay, so first is you assign, so if there are 3 loops, you assign your I1, I2 and I3. Okay, and then you apply Kirchhoff's voltage law to each of the n meshes, and then you use Ohm's law again, expressing in terms of voltage, meaning V is equal to IR. Like how it was in node, we used to do I is equal to V upon R. Over here we'll be using V is equal to IR. Okay. Then you solve the equations using simultaneous equations or matrix or any other method that you feel comfortable with. Okay. So let's look at this example. So if you look at this example, now let's look at mesh 1. Okay, so this is my mesh 1, mesh 2 and mesh 3. So that's I1, I2, I3. For my mesh 1, it is minus 24 volt if you're going from this side. So minus 24 volt. And then now it's going to this 10 ohm resistor. So since there is 2 currents involved now, what I'll do is I'll do 10 into I1 minus I2. Okay, so that's how you get this. Then you add that to 12 into I1 minus I3. Okay, so note that there is also a dependent source, and whatever value this source has will be dependent heavily on this current, on this branch that has been given to us by the question. Okay. Okay. So let's look at mesh 2 now. Mesh 2, it says 24 I1 plus 4 into I2 minus I3. Why I2 minus I3? Because this 4 ohm resistor has 2 currents involved. So you do I2 minus I3 since this is the branch you're focusing on. And then you do 10 into I2 minus I1. Now it will be I2 minus I1. In mesh 1 it was I1 minus I2. We do that because now our focus is more on the mesh 2, on the branch or the loop 2. Okay. Now for the third mesh, okay, so it will be 4 into I3 minus I1, I2 plus 4 I0. Okay. Note I0, the value for I0 is sum of current entering is equal to sum of current leaving, so this will become I1 minus I2. Okay, I1 minus I2. Okay. So solving that using matrix, this is what you should be expecting to get, okay, as your output result. And now let's look at another scenario of this, which is super mesh. So what is a super mesh? So just like what we saw in node analysis, that if there is a voltage source between 2 nodes, it becomes a super node. Here, when there is a current source between 2 meshes, okay, a super mesh is required because mesh analysis is just KVL, but the voltage across the current source cannot be known in advance. Okay. So if a super mesh consists of 2 meshes, 2 equations are needed. One is obtained using KVL and Ohm's law to the super mesh. Okay. So if there is a current supply between two meshes, we remove that and do a normal calculation. Okay. Like for example, let's look at this example. This is our final example for today. And it says, for the current in figure below, find I1 to I4. I1 to I4. Why I1 to I4? Because there is 4 different. 1, 2, 3, 4. There is 4 different loops. Okay. Alright. So note that there is 1 and 2. There is 2 super meshes that are involved. Okay. So we remove these 2 and this becomes only 1. Okay. So if you look at it, so now this is 2I1 plus 4I3 plus 8 into I3 minus I4 plus 6I2 will give me 0. Okay. So now applying Kirchhoff's current law, at node P. Okay, so this is node P. Okay, we get I2 is equal to I1 plus 5. So this is using just this sum of Kirchhoff's current rule actually. Okay, and at Q it's I2 is equal to I3 plus 3 I0. And note that since I0 is given to us and I4 is in the opposite direction, so whatever value we have for I4 will be our value for I0. So this is, let's say if we get negative 3 for our I4, so our I0 will be positive 3. Okay. So once we have all four equations, what we have to do is to solve the equations 1 to 4 using any of the methods that is convenient to you. You should be able to get I1 as minus 7.5, I2 as minus 2.5, I3 as 3.93, and I4 as 2.143. Okay. So this is the mentoring session that I had prepared for us today. Thank you very much for your time. And I hope that you have learned something in preparation for your exam, which is this Friday. Good luck with